Welcome to GTC. We have a lot to cover with you today. GTC is where we talk about industry, science, computing, the present, and the future. NVIDIA invented a new computing model for the first time in 60 years, as you saw in the video. A new computing model rarely comes about. It takes an enormous amount of time and set of conditions. We invented this computing model because we wanted to solve problems that general purpose computers, normal computers, could not. We also observed that someday transistors will continue, the number of transistors will grow, but the performance and the power of transistors will slow down. That Moore's law will not continue beyond, limited by the laws of physics. And that moment has now arrived. Dennard scaling has stopped. It's called Dennard scaling. Dennard scaling has stopped nearly a decade ago. And in fact, the transistor performance and its power associated has slowed tremendously. And yet, the number of transistors continued. We made this observation a long time ago, and for 30 years, we've been advancing this form of computing we call accelerated computing. We invented the GPU. We invented the programming model called CUDA, and we observed that if we could add a processor that takes advantage of more and more and more transistors, apply parallel computing, add that to a sequential processing CPU, that we could extend the capabilities of computing well beyond. And that moment has really come. We have now seen that inflection point. Accelerated computing, its moment has now arrived. This is the treasure of our company. Most people talk about the GPU. The GPU is important, but without a programming model that sits on top of it, and without dedication to that programming model, keeping it compatible over generations. We're now CUDA 13 coming up on CUDA 14. Hundreds of millions of GPUs running in every single computer, perfectly compatible. If we didn't do that, then developers wouldn't target this computing platform. If we didn't create these libraries, then developers wouldn't know how to use the algorithm and use the architecture to its fullest. One application after another. I mean, this is really the treasure of our company. cuLitho, computational lithography. It took us nearly 7 years to get here with cuLitho, and now TSMC uses it, Samsung uses it, ASML uses it. This is an incredible library for computational lithography, the first step of making a chip. Sparse solvers for CAE applications. cuOpt, a numerical optimization, has broken just about every single record. The traveling salesperson problem, how to connect millions of products with millions of customers in the supply chain. Warp, Python solver for CUDA, for simulation. cuDF, a data frame approach, basically accelerating SQL, data frame databases. This library is the one that started AI altogether, cuDNN. The library on top of it, called Megatron Core, made it possible for us to simulate and train extremely large language models. The list goes on. MONAI, really important. The #1 medical imaging AI framework in the world. By the way, we're not going to talk a lot about healthcare today, but be sure to see Kimberly's keynote. She's going to talk a lot about the work that we do in healthcare. And the list goes on. Genomics processing, Ariel, pay attention. We're going to do something really important here today. cuQuantum, quantum computing. This is just a representative of 350 different libraries in our company. And each one of these libraries redesigned the algorithm necessary for accelerated computing. Each one of these libraries made it possible for all of the ecosystem partners to take advantage of accelerated computing. And each one of these libraries opened new markets for us. Let's take a look at what CUDA X can do.
Ready, go!
Is that amazing? Everything you saw was a simulation. There was no art, no animation. This is the beauty of mathematics. This is deep computer science, deep math, and it's just incredible how beautiful it is. Every industry was covered, from healthcare and life sciences to manufacturing, robotics, autonomous vehicles, computer graphics, even video games. That first shot that you saw was the first application NVIDIA ever ran. And that's where we started in 1993. And we kept believing in what we were trying to do. And it's hard to imagine that you could see that first virtual fighter scene come alive. And that same company believed that we would be here today. It's just a really, really incredible journey. I want to thank all the NVIDIA employees for everything that you've done. It's really incredible. Telecommunications is the backbone, the lifeblood of our economy, our industries, our national security. And yet, ever since the beginning of wireless, where we defined the technology, we defined the global standards, we exported American technology all around the world so that the world can build on top of American technology and standards. Today, we're announcing that we're going to do that. We have a big partnership with Nokia. Nokia is the second largest telecommunications maker in the world. It's a $3 trillion industry. Infrastructure is hundreds of billions of dollars. There are millions of base stations around the world. If we could partner, we could build on top of this incredible new technology, fundamentally based on accelerated computing and AI, and for the United States, for America to be at the center of the next revolution in 6G. So today we're announcing that NVIDIA has a new product line. It's called the NVIDIA ARC, the Aerial Radio Network Computer. Aerial RAN Computer, ARC. ARC is built from three fundamental new technologies: the Gray CPU, the Blackwell GPU, and our ConnectX, Mellanox ConnectX networking designed for this application. And all of that makes it possible for us to run this library, this CUDA-X library that I mentioned earlier called Aerial. Aerial is essentially a wireless communication system running on top of CUDA-X. We're gonna create, for the first time, a software-defined, programmable computer that's able to communicate wirelessly and do AI processing at the same time. This is completely revolutionary. We call it NVIDIA ARC. And Nokia is going to work with us to integrate our technology, rewrite their stack. This is a company with 7,000 fundamental, essential 5G patents. Hard to imagine any greater leader in telecommunications. So we're going to partner with Nokia. They're going to make NVIDIA ARC their future base station. NVIDIA ARC is also compatible with AirScale, the current Nokia base stations. So what that means is we're going to take this new technology and we'll be able to upgrade millions of base stations around the world with 6G and AI. Let's talk about quantum computing. We now realize that it's essential for us to connect a quantum computer directly to a GPU supercomputer so that we could do the error correction, so that we could do the artificial intelligence calibration and control of the quantum computer, and so that we could do simulations collectively, working together, the right algorithms running on the GPUs, the right algorithms running on the QPUs, and the two processors, the two computers working side by side. This is the future of quantum computing. Let's take a look.
There are many ways to build a quantum computer. Each uses qubits, quantum bits, as its core building block. But no matter the method, all qubits, whether superconducting qubits, Trapped ions, neutral atoms or photons, share the same challenge. They're fragile and extremely sensitive to noise. Today's qubits remain stable for only a few hundred operations, but solving meaningful problems requires trillions of operations. The answer is quantum error correction. Measuring disturbs a qubit, which destroys the information inside it. The trick is to add extra qubits, entangle, so that measuring them gives us enough information to calculate where errors occurred without damaging the qubits we care about. It's brilliant, but needs beyond state-of-the-art conventional compute. That's why we built NVQLink, a new interconnect architecture that directly connects quantum processors with NVIDIA GPUs. Quantum error correction requires reading out information from qubits, calculating where errors occur, and sending data back to correct them. NVQLink is capable of moving terabytes of data to and from quantum hardware, the thousands of times every second needed for quantum error correction. At its heart is CUDA-Q, our open platform for quantum GPU computing. Using NVQLink and CUDA-Q, researchers will be able to do more than just error correction. They will also be able to orchestrate quantum devices and AI supercomputers to run quantum GPU applications. Quantum computing won't replace classical systems. They will work together, fused into one accelerated quantum supercomputing platform.
Today, we're announcing the NVQLink. Remember, CUDA was designed for GPU, CPU, accelerated computing. Basically using both processors to use the right tool to do the right job. Now, CUDA-Q has been extended beyond CUDA so that we could support QPU and have the two processors, QPU and the GPU, work and have computation move back and forth within just a few microseconds. The essential latency to be able to cooperate with the quantum computer. So now CUDA-Q is such an incredible breakthrough adopted by so many different developers. We are announcing today 17 different quantum computer industry companies supporting the NVQLink. And I'm so excited about this, 8 different DOE labs, Berkeley, Brookhaven, Fermi Labs in Chicago, Lincoln Laboratory, Los Alamos, Oak Ridge, Pacific Northwest, San Diego National Lab. Just about every single DOE lab has engaged us, working with our ecosystem of quantum computer companies and these quantum controllers so that we could integrate quantum computing into the future of science. Well, I have one more additional announcement to make. Today, we're announcing that the Department of Energy is partnering with NVIDIA to build 7 new AI supercomputers to advance our nation's science. AI is a lot more. AI is, in fact, I'm going to describe AI in a couple different ways. The first way you think about AI is that it has completely reinvented the computing stack. The way we used to do software was hand coding software running on CPUs. Today, AI is machine learning, training, data-intensive programming, if you will, trained and learned by AI that runs on a GPU. The software of the past, and this is a profound understanding, a profound observation of artificial intelligence, that the software industry of the past was about creating tools. Excel is a tool. Word is a tool. A web browser is a tool. The reason why I know these are tools is because you use them. The tools industry, just as screwdrivers and hammers, the tools industry is only so large. In the case of IT tools, they could be database tools. These IT tools is about $1 trillion or so. But AI is not a tool. AI is work. That is the profound difference. AI is, in fact, workers that can actually use tools. One of the things I'm really excited about is the work that Ervin's doing at Perplexity. Perplexity using web browsers to book vacations or do shopping. Basically an AI using tools. Cursor is an AI, an agentic AI system that we use at NVIDIA. Every single software engineer at NVIDIA uses Cursor. Has improved our productivity tremendously. It's basically a partner for every one of our software engineers to generate code. And it uses a tool. And the tool it uses is called VS Code. So Cursor is an AI, agentic AI system that uses VS Code. Well, all of these different industries, whether it's chatbots or digital biology, where we have AI assistant researchers, or what is a robo-taxi? Inside a robo-taxi, of course, it's invisible, but obviously there's a AI chauffeur. That chauffeur is doing work, and the tool that it uses to do that work is the car. Everything that we've made up until now are tools for us to use. For the very first time, technology is now able to do work and help us be more productive. In this new world, there needs to be a computer that understands context all the time. It can't pre-compute that. Because every time you use the computer for AI, every time you ask the AI to do something, the context is different. So it has to process all of that information. Environmental, for example, in the case of a self-driving car, it has to process the context of the car. Context processing. What is the instruction you're asking the AI to do? Then it's got to go and break down the problem step by step, reason about it, and come up with a plan and execute it. Every single one at that step requires enormous number of tokens to be generated, which is the reason why we need a new type of system, and I call it an AI factory. It's an AI factory for sure. It's unlike a data center of the past. It's an AI factory because this factory produces one thing. Unlike the data centers of the past that does everything, stores files for all of us, runs all kinds of different applications. You could use that data center like you can use your computer for all kinds of applications. You could use it to play a game one day, you could use it to browse the web, you could use it, to do your accounting. And so that is a computer of the past, a universal general purpose computer. The computer I'm talking about here is a factory. It runs basically one thing, it runs AI, and its purpose is designed to produce tokens that are as valuable as possible, meaning they have to be smart. And you want to produce these tokens at incredible rates, because when you ask an AI for something, you would like it to respond. And notice, during peak hours, these AIs are now responding slower and slower because it's got a lot of work to do for a lot of people. And so you want it to produce valuable tokens at incredible rates, and you want it to produce it cost effectively. Every single word that I used are consistent with an AI factory, with a car factory, or any factory. It is absolutely a factory. And these factories never existed before. NVLink 72, if we were to create one giant chip, one giant GPU, this is what it would look like. This is the level of wafer scale processing we would have to do. It's incredible. All of these chips are now put into one giant rack. This one giant rack makes all of these chips work together as one. This is what we created in the past. This is NVLink 8. Now, these models are so gigantic, the way we solve it is we turn this gigantic model, into a whole bunch of experts. It's a little bit like a team. And so these experts are good at certain types of problems, and we collect a whole bunch of experts together. And so this giant multi-trillion-dollar AI model has all these different experts, and we put all these different experts on a GPU. Now, this is NVLink 72. We could put all of the chips into one giant fabric, and every single expert can talk to each other. So the master, the primary expert, could talk to all of the distributed work and all of the necessary context and prompts and bunch of data that we have to, bunch of tokens that we have to send to all of the experts. The experts would, whichever one of the experts are selected to solve the answer, would then go off and try to respond. and then it would go off and do that layer after layer after layer. Here, NVLink 72, we have 72 GPUs. We have one GPU generating thinking for 4 experts, versus here, because each one of the computers can only put 8 GPUs, we have to put 32 experts into one GPU. So this one GPU has to think for 32 experts, versus this system, each GPU only has to think for 4. And because of that, the speed difference is incredible. And this just came out. This is the benchmark done by Semi-Analysis. They do a really, really thorough job. And they benchmarked all of the GPUs that are benchmarkable. And it turns out it's not that many. If you look at the list of GPUs you could actually benchmark, is like 90% NVIDIA. Okay? So we're comparing ourselves to ourselves, but the second best GPU in the world is the H200 and runs all the workload. Grace Blackwell per GPU is 10 times the performance. Now, how do you get 10 times the performance when it's only twice the number of transistors? Well, the answer is extreme co-design. And by understanding the nature of the future of AI models, and we're thinking across that entire stack, we can create architectures for the future. This is a big deal. It says we can now respond a lot faster, but this is an even bigger deal. This next one, look at this. This says that the lowest cost tokens in the world are generated by Grace Blackwell NVLink 72, the most expensive computer. On the one hand, GB200 is the most expensive computer. On the other hand, its token generation capability is so great that it produces it at the lowest cost, because the tokens per second divided by the total cost of ownership of Grace Blackwell is so good. It is the lowest cost way to generate tokens. By doing so, delivering incredible performance, 10 times the performance, delivering 10 times lower cost, that virtuous cycle can continue. This is what's going on in our company's business. We're seeing extraordinary growth for Grace Blackwell for all the reasons that I just mentioned. It's driven by 2 exponentials. We now have visibility. I think we're probably the first technology company in history to have visibility into $500 billion of cumulative Blackwell and early ramps of Rubin through 2026. This is how much business is on the books. $500 billion worth so far. Now this is, out of that, we've already shipped 6 million of the Blackwells in the first several quarters. I guess the first 4 quarters of production, 3.5 quarters of production. We still have 1 more quarter to go for 2025, and then we have 4 quarters. So the next 5 quarters, there's $500 billion, $500 billion. That's 5 times the growth rate of Hopper. That kind of tells you something. This is Hopper's entire life. This doesn't include China and Asia, so this is just the West, okay? This is just, we're excluding China. So Hopper, in its entire life, 4 million GPUs. Blackwell, each one of the Blackwells has 2 GPUs in it in one large package. 20 million GPUs of Blackwells in the early parts of Rubin. Incredible growth.
The age of AI has begun. Blackwell is its engine, an engineering marvel. In Arizona, it starts as a blank silicon wafer. Hundreds of chip processing and ultraviolet lithography steps build up each of the 200 billion transistors, layer by layer on a 12-inch wafer. In Indiana, HBM stacks will be assembled in parallel. HBM memory dies with 1,024 IOs are fabricated using advanced EUV technology. Through silicon via is used in the backend to connect 12 stacks of HBM memory and base die to produce HBM. Meanwhile, the wafer is scribed into individual Blackwell die, tested and sorted, separating the good dies to move forward. The chip-on-wafer on substrate process attaches 32 Blackwell dies and 128 HBM stacks on a custom silicon interposer wafer. Metal interconnect traces are etched directly into it, connecting Blackwell GPUs and HBM stacks into each system and package unit, locking everything into place. Then the assembly is baked, molded, and cured, creating the GB300 Blackwell Ultra superchip. In Texas, robots will work around the clock to pick and place over 10,000 components onto the Grace Blackwell PCB. In California, Connect X8 Super NICs for scale-out communications and Bluefield 3 DPUs for offloading and accelerating networking, storage, and security are carefully assembled into GB300 compute trays. NVLink is the breakthrough high-speed link that NVIDIA invented to connect multiple GPUs and scale up into a massive virtual GPU. The NVLink switch tray is constructed with NVLink switch chips, providing 14.4 terabytes per second of all-to-all bandwidth. NVLink spines form a custom blind-mated backplane with 5,000 copper cables connecting all 72 Blackwells, or 144 GPU dies, into one giant GPU, delivering 130 terabytes per second of all-to-all bandwidth, nearly the global internet's peak traffic. Skilled technicians assemble each of these parts into a rack-scale AI supercomputer. In total, 1.2 million components, 2 miles of copper cable, 130 trillion transistors, weighing nearly 2 tons. From silicon in Arizona and Indiana to systems in Texas, Blackwell and future NVIDIA AI factory generations will be built in America. Writing a new chapter in American history and industry. America's return to making and reindustrialization, reignited by the age of AI. The age of AI has begun. Made in America. Made for the world.
In order for us to do co-design now, look at all of the chips we have to do. This is what it takes. You're not going to take one chip and make a computer 10 times faster. That's not going to happen. The way to make computers 10 times faster, that we can keep increasing the performance exponentially, we can keep driving costs down exponentially, is extreme co-design and working on all these different chips at the same time. We now have Rubin back home. This is Rubin. This is the Vera Rubin and Rubin. Ladies and gentlemen, Rubin. This is our third generation NVLink 72 rack scale computer. Third generation. GB200 was the first one. All of our partners around the world, I know how hard you guys worked. It was insanely hard. It was insanely hard to do. Second generation, so much smoother. And this generation, look at this, completely cableless. Completely cableless. And this is all back in the lab now. This is the next generation Rubin. While we're shipping GB300s, we're preparing Rubin to be in production, this time next year, maybe slightly earlier. And so every single year, we are going to come up with the most extreme co-design system so that we can keep driving up performance and keep driving down the token generation cost. Look at this. This is just an incredibly beautiful computer. Now, so this is amazing. This is 100 petaflops. I know it doesn't mean anything. 100 petaflops. But compared to the DGX1 I delivered to OpenAI 9 years ago, it's 100 times the performance right here versus 100 times of that supercomputer. 100 times, 100 of those, let's see, 100 of those would be like 25 of these racks, all replaced by this one thing. One Vera Rubin. Okay, so this is the compute tray. If you decide you wanted to add a special processor, we've added another processor. It's called a context processor because the amount of context that we give AIs are larger and larger. We wanted to read a whole bunch of PDFs before it answered a question. We wanted to read a whole bunch of archive papers, watch a whole bunch of videos. Go learn all this before you answer a question for me. All of that context processing could be added. You have Bluefield 4, this new data processor, 2 Vera CPUs, and 4 Rubin packages, or 8 Rubin GPUs. All of that in this one node, completely cable-less, 100% liquid-cooled. And then this new processor, I won't talk too much about it today, I don't have enough time, but this is completely revolutionary. And the reason for that is because your AIs need to have more and more memory. You're interacting with it more, you wanted to remember our last conversation, everything that you've learned on my behalf, please don't forget it when I come back next time. And so all of that memory is going to create this thing called KV caching, and that KV caching, retrieving it, you might have noticed, every time you go into your AIs these days, it takes longer and longer to refresh and retrieve all of the previous conversations. And the reason for that is that we need a revolutionary new processor, and that's called Bluefield 4. Next, the NVLink switch, which is right here. Okay? This is the NVLink switch. This is what makes it possible for us to connect all of the computers together. And this switch is now several times the bandwidth of the entire world's peak internet traffic. And so that spine is going to communicate and carry all of that data simultaneously to all of the GPUs. On top of that, this is the Spectrum X switch, and this Ethernet switch was designed so that all of the processors could talk to each other at the same time and not gum up the network. As you notice, NVIDIA started out by designing chips, and then we started to design systems, and we designed AI supercomputers. Now we're designing entire AI factories. Every single time we move out and we integrate more of the problem to solve, we come up with better solutions. We now build entire AI factories. This AI factory is what we're building for Vera Rubin, and we created a technology that makes it possible for all of our partners to integrate into this factory digitally. Let me show it to you.
The next industrial revolution is here. And with it, a new kind of factory. AI infrastructure is an ecosystem-scale challenge, requiring hundreds of companies to collaborate. NVIDIA Omniverse DSX is a blueprint for building and operating gigascale AI factories. For the first time, the building, power, and cooling are co-designed with NVIDIA's AI infrastructure stack. It starts in the Omniverse digital twin. Jacobs Engineering optimizes compute density and layout to maximize token generation according to power constraints. They aggregate SIM-ready OpenUSD assets from Siemens, Schneider Electric, Trane, and Vertiv into PTC's product lifecycle management. Then simulate thermals and electricals with CUDA accelerated tools from ETAP and Cadence. Once designed, NVIDIA partners like Bechtel and Vertiv deliver prefabricated modules, factory-built, tested, and ready to plug in. This shrinks build time significantly, achieving faster time to revenues. When the physical AI factory comes online, the digital twin acts as an operating system. Engineers prompt AI agents from Phaidra and Emerald AI, previously trained in the digital twin, to optimize power consumption and reduce strain on both the AI factory and the grid. In total, for a 1 gigawatt AI factory, DSX optimizations can deliver billions of dollars in additional revenue per year. across Texas, Georgia, and Nevada. NVIDIA's partners are bringing DSX to life. In Virginia, NVIDIA is building an AI factory research center using DSX to test and productize Vera Rubin, from infrastructure to software. With DSX, NVIDIA partners around the world can build and bring up AI infrastructure faster than ever.
In order to do it for physical AI, you need 3 computers. You need the computer to train it. This is GB, the Grace Blackwell NVLink 72. We need a computer that does all of the simulations that I showed you earlier with Omniverse DSX. It basically is a digital twin for the robot to learn how to be a good robot and for the factory to essentially be a digital twin. That computer is the second computer, the Omniverse computer. This computer has to be incredibly good at generative AI, and it has to be good at computer graphics, sensor simulation, ray tracing, signal processing. This computer is called the Omniverse computer. And once we train the model, simulate that AI inside a digital twin, and that digital twin could be a digital twin of a factory, as well as a whole bunch of digital twins of robots. Then you need to operate that robot, and this is the robotic computer. This one goes into a self-driving car. Half of it could go into a robot, okay? Or you could actually have, robots that are quite agile and quite fast in operations, and it might take 2 of these computers. And so this is the Jetson Thor robotics computer. These 3 computers all run CUDA, and it makes it possible for us to advance physical AI that understand the physical world, understand laws of physics, causality, and these robots also need the physical AI, applies physical AI, and works inside the digital twin. Let's take a look at it.
America is reindustrializing, reshoring manufacturing across every industry. In Houston, Texas, Foxconn is building a state-of-the-art robotic facility for manufacturing NVIDIA AI infrastructure systems. With labor shortages and skills gaps, digitalization, robotics, and physical AI are more important than ever. The factory is born digital in Omniverse. Foxconn engineers assemble their virtual factory in a Siemens digital twin solution developed on Omniverse technologies. Every system, mechanical, electrical, plumbing, is validated before construction. Siemens plant simulation runs design space exploration optimizations to identify ideal layout. When a bottleneck appears, engineers update the layout, with changes managed by Siemens Team Center. In Isaac Sim, the same digital twin is used to train and simulate robot AIs. In the assembly area, FANUC manipulators build GB300 tray modules. Bimanual manipulators from FII and Skilled AI install bus bars into the trays, and AMRs shuttle the trays to the test pods. Then, Foxconn uses Omniverse for large-scale sensor simulation, where robot AIs learn to work as a fleet. In Omniverse, Vision AI agents built on NVIDIA Metropolis and Cosmos watch the fleets of robots and workers from above to monitor operations and alert Foxconn engineers of anomalies and safety violations, or even quality issues. And to train new employees, agents power interactive AI coaches for easy worker onboarding. The age of U.S. reindustrialization is here, with people and robots working together.
These factories will have future robotic systems. And one of the most advanced is Figure. Brett Adcock is here today. He founded a company 3.5 years ago. They're worth almost $40 billion today. We're working together in training the AI, training the robot, simulating the robot, and of course, the robotic computer that goes into Figure. Really amazing. I had the benefit of seeing it. It's really quite extraordinary. It is very likely that humanoid robots, and my friend Elon is also working on this, that this is likely going to be one of the largest new consumer electronics markets, and surely one of the largest industrial equipment market. Peggy Johnson and the folks at Agility are working with us on robots for warehouse automation. The folks at Johnson & Johnson working with us again, training the robot, simulating it in digital twins, and also operating the robot. These Johnson & Johnson surgical robots are even going to perform surgery that are completely non-invasive surgery at a precision the world's never seen before. And of course, the cutest robot ever, the Disney robot. And this is something really close to our heart. We're working with Disney Research on an entirely new framework and simulation platform based on revolutionary technology called Newton. And that Newton simulator makes it possible for the robot to learn how to be a good robot inside a physically aware, physically based environment. Let's take a look at it. Ladies and gentlemen, Disney Blue. Tell me that's not adorable. He's not adorable. We all want one. We all want one. Now, remember, everything you were just seeing, that is not animation. It's not a movie. It's a simulation. That simulation is an Omniverse. Omniverse, the digital twin. So these digital twins of factories, digital twins of warehouses, digital twins of surgical rooms, digital twins where Blue could learn how to manipulate and navigate and interact with the world, all completely done in real time. This is going to be the largest consumer electronics product line in the world. Some of them are just really working incredibly well now. This is the future of humanoid robotics, and of course, Blue. Humanoid robots is still in development, but meanwhile, there's one robot that is clearly at an inflection point, and it is basically here, and that is a robot on wheels. This is a robo-taxi. A robo-taxi is essentially an AI chauffeur. Now, one of the things that we're doing today, we're announcing the NVIDIA DRIVE Hyperion. This is a big deal. We created this architecture so that every car company in the world could create cars. Vehicles could be commercial, could be passenger, could be just dedicated to robo-taxi. Create vehicles that are robo-taxi ready. The sensor suite with surround cameras and radars and LiDAR make it possible for us to achieve the highest level of surround cocoon sensor perception and redundancy necessary for the highest level of safety. Hyperion Drive Hyperion, is now designed into Lucid, Mercedes-Benz, my friend Ola Kalenius, the folks at Stellantis, and there are many other cars coming. And once you have a basic standard platform, then developers of AV systems, and there's so many talented ones, Wave, Wabi, Aurora, Momenta, Neuro, there's so many of them. WeRide, there's so many of them that can then take their AV system and run it on the standard chassis. Basically, the standard chassis has now become a computing platform on wheels. And because it's standard and the sensor suite is comprehensive, all of them could deploy their AI to it. Let's take a quick look. Okay, that's beautiful San Francisco. And as you could see, robo-taxi's inflection point is about to get here. And in the future, 1 trillion miles a year that are driven, 100 million cars made each year. There's some 50 million taxis around the world. It's going to be augmented by a whole bunch of robo-taxis. So it's going to be a very large market. To connect it and deploy it around the world, today we're announcing a partnership with Uber. Uber, Dara is going to, we're working together to connect these NVIDIA DRIVE Hyperion cars into a global network. And now in the future, you'll be able to hail up one of these cars, and the ecosystem is going to be incredibly rich, and we'll have Hyperion or robo-taxi cars all over the world. This is going to be a new computing platform for us, and I'm expecting it to be quite successful.